Topic: The philosophical implications of quantum physics. Answers to big questions of life. Quantum physics, the study of the smallest particles in the universe, has transformed our understanding of reality. It challenges the deterministic worldview of classical physics and introduces new concepts such as wave-particle duality, uncertainty, and entanglement. These phenomena not only defy common sense but also open up profound philosophical questions about the nature of reality, causality, and the role of the observer in the universe. In this video, we will explore the philosophical implications of quantum physics. The shift from classical to quantum worldview. Classical physics, the deterministic universe. Before the advent of quantum mechanics, classical physics, particularly Newtonian mechanics, dominated the scientific worldview. In this deterministic framework, the universe operated like a vast machine governed by fixed laws. Every event had a cause, and sufficient information could predict the future with absolute certainty. This deterministic view provided a clear, orderly, and predictable model of reality. Quantum physics, the emergence of uncertainty. Quantum physics shattered the deterministic worldview by revealing that particles do not behave in a predictable, deterministic manner at the subatomic level. The uncertainty principle, formulated by Werner Heisenberg, states that one cannot simultaneously know a particle's position and momentum with absolute precision. This inherent uncertainty suggests that probabilities rather than certainties govern the universe at its most fundamental level. The implications of this are profound. If the behavior of particles is inherently uncertain, then the deterministic clockwork universe of classical physics no longer holds. The future is not fixed, and events at the quantum level can only be described in terms of probabilities. This introduces a level of indeterminacy into our understanding of reality, challenging the classical notion of causality. The role of the observer effect in quantum mechanics. One of the most striking philosophical implications of quantum physics is the role of the observer. In classical physics, the act of observation is passive. The universe exists independently of whether or not we observe it. However, in quantum physics, the act of observation plays a crucial role in determining the outcome of quantum events. This is famously demonstrated in the double-slit experiment, where particles behave differently depending on whether or not they are observed. This observer effect raises profound philosophical questions about the nature of reality. Does reality exist independently of observation, or is it in some way created by the act of observation? If the latter is true, then the boundary between subject and object, observer and observed, becomes blurred, challenging the traditional view of an objective, observer-independent reality. Consciousness and reality. The question of the observer in quantum mechanics leads to deeper philosophical questions about the nature of consciousness. If the act of observation influences the outcome of quantum events, then what role does consciousness play in shaping reality? Some interpretations of quantum mechanics suggest that consciousness is fundamental to the structure of reality, implying that the universe is not just a collection of physical objects but also involves the consciousness of observers. This idea aligns with certain philosophical and spiritual traditions that view consciousness as a fundamental aspect of existence. For example, Georg Unger, in Basic Concepts of Modern Physics, explores the relationship between physics and spiritual science, suggesting that an understanding of the spiritual or consciousness aspects of reality must complement our understanding of the physical world. Quantum entanglement and non-locality. The mystery of entanglement. Quantum entanglement is one of the most mysterious and counterintuitive phenomena in quantum physics. When two particles become entangled, their states become linked in such a way that the state of one particle instantly influences the state of the other, regardless of the distance between them. This phenomenon, which Einstein famously referred to as spooky action at a distance, seems to violate the principle of locality, which states that objects can only be influenced by their immediate surroundings. Implications for causality and reality. Entanglement challenges our classical understanding of causality and suggests that the universe is more interconnected than previously thought. It raises the question of whether space and time are fundamental structures of reality or emergent properties of a deeper, non-local quantum reality. If entangled particles can influence each other instantaneously across vast distances, then the notion of causality as a chain of local events breaks down. Philosophically, this challenges our understanding of separateness and individuality. If particles are fundamentally interconnected, then perhaps everything in the universe is interconnected at some deep level. This idea resonates with certain philosophical and spiritual traditions that emphasize the interconnectedness of all things. The search for a unified theory, incompatibility of quantum mechanics and general relativity. One of the major challenges in modern physics is the incompatibility between quantum mechanics and general relativity. While quantum mechanics successfully describes the behavior of particles at the smallest scales, general relativity describes the behavior of massive objects and the structure of space-time at the largest scales. However, these two theories are fundamentally incompatible, and physicists have been searching for a unified theory that can reconcile them. Philosophical implications of a unified theory. The search for a unified theory raises philosophical questions about knowledge's nature and scientific understanding's limits. If such a theory were discovered, it would provide a comprehensive description of the universe, answering many of the questions that have puzzled scientists and philosophers for centuries. However, it would also raise new questions about the nature of reality and the relationship between science and philosophy. In Brief Answers to the Big Questions, Stephen Hawking reflects on the possibility of discovering a unified theory, acknowledging that while it may provide answers to many scientific questions, it may also leave certain philosophical questions unresolved. For example, even if we understand how the universe works, we may still not know why it exists or what its ultimate purpose is. These are questions that lie beyond the realm of science and enter the domain of philosophy. The nature of time. Time in classical and quantum physics. Time has been a central concept in classical and quantum physics, but the two frameworks offer very different conceptions. In classical physics, time is linear and absolute, moving steadily forward. However, in the realm of quantum mechanics and relativity, time is not so straightforward. Einstein's theory of relativity shows that time is relative to the observer's frame of reference and can even slow down or speed up depending on the observer's velocity and the strength of gravitational fields. Quantum physics further complicates our understanding of time by introducing the possibility that time may not be a fundamental aspect of reality but an emergent property. In this view, time may not exist at the quantum level, and the flow of time may be a macroscopic illusion that emerges from a deeper, timeless reality. The arrow of time and free will. The arrow of time, the idea that time flows in one direction, from past to future, is closely related to the second law of thermodynamics, which states that entropy, or disorder, always increases. However, quantum mechanics raises the possibility that the arrow of time may not be as fixed as it appears. If the laws of physics are reversible at the quantum level, then time could theoretically flow backward. This raises profound philosophical questions about free will and determinism. If time can flow in either direction, then what does this mean for our understanding of cause and effect? Do past events determine our actions, or do we have the ability to shape the future through free will? These are questions that continue to be debated by both scientists and philosophers. Conclusion: quantum physics has not only transformed our understanding of the physical universe but has also opened up new philosophical questions about the nature of reality, causality, consciousness, and time. By challenging the deterministic worldview of classical physics and introducing concepts such as uncertainty, entanglement, and the role of the observer, quantum mechanics has reshaped the way we think about the universe and our place within it. While books like A Brief History of Time and Brief Answers to the Big Questions by Stephen Hawking focus on explaining these scientific concepts to a general audience, works like Basic Concepts of Modern Physics by Georg Unger explore the deeper philosophical implications of these ideas. Together, these works invite us to reflect on the mysteries of the universe and the limits of human knowledge, reminding us that the more we learn, the more questions we uncover. References: Hawking, Stephen, A Brief History of Time, Bantam Books, 1988. Unger, Georg, Basic Concepts of Modern Physics, Steiner Books, 2024. Hawking, Stephen, Brief Answers to the Big Questions, Bantam Books, 2018. Thanks for watching. Don't forget to subscribe to the channel for your success. If you like this video, please give it a thumbs up.